Hello, my name is Ojit and I worked on the design project and I worked with a group members whose names are on the slide. Here's an image of our group. This project aims to invest combined piezoelectric thermal resonant cantilever designed to achieve high transfer tip displacement. The cantilever consists of piezoelectric material wrapped with varying metals such as titanium, gold, brass, and fictional vibranium on top and bottom faces. Brass is chosen for its resonant properties, while vibranium is approximated with tantalum alloy. Metal thickness is varied to identify large tip displacement and equilibrium temperature at the junction. The cantilever is actuated by a fixed voltage, producing movement through the piezoelectric effect and internal heat generation. The piezoelectric has a specific dimension compliance piezoelectric strain component matrix, permittivity matrix, thermal expansion coefficient, and density. The ambient temperature is 25 degrees Celsius. The project aims to determine the resonant frequency of best performing dimensions for each material. I primarily focused on writing the report. The goal of this project is to optimize the thickness of the metal portions around piezoelectric materials to maximize transfer dip displacement while considering constraints such as temperature and voltage. The problem is simplified to 2D, eliminating the y-axis and using the x and the z-axis for simulation. Stiffness measures for both piezoelectric and polymer material are obtained, and Hooke's law is used to relate strains to stresses. The code from DA4 is modified to include region from the metal portions and incorporate techniques from topic 2's notes for forward piezoelectric effect and heat transfer. The model aims to account for convection and the anchor and curved electric field around the tip of the metal portion. The objective is to find optimal thickness for the metal portions to result in maximum transfer tip displacement, taking into account mechanical strain, temperature difference, and electric field, while considering constraints and utilizing knowledge from previous assignment literature. The model has been validated using several methods. First, the piezoelectric portion of the model has been validated, setting up the model to use the same conditions and material properties as those of DA4 and comparing displacements with the original code. Displacement produced by the piezoelectric and thermal expansion alone was in the line of DA4 code, validating the geometry of the model. The plotting functionality was used to validate the electric field and voltage plots. The electric field and plots showed that field was applied correct direction, with the most going through the piezoelectric as expected. The voltage plot also showed that the model was working correctly, and with the voltage gradient becoming distorted as contacts moved away from the left where the dielectric was between the metal layers. The thermal stress were validated by plotting heat flux temperature. The heat flux plot showed the flux was mostly across the conductor outwards from the structure, which was expected. The temperature plot showed the temperature was highest near the anchor and top corner where the conductor was thin and dissipating less heat. The model analysis, which involved mostly simple modification to the material properties of DA5 code, was validated by finding the first mode frequency using established methods. The resonant frequency was found to be dependent on the shape material of the structure and not the external stress applied, as confirmed by changing the values of the electric field and temperature difference without affecting the frequency output. Based on the above evidence, it can be concluded that the developed model is accurate to a certain degree and validated using various methods. The flex code here was constructed to validate the model, which corroborates with the results and the theoretical calculated values within a certain degree. Validation methods outlined confirm that the model is accurate and can be relied upon for further analysis. Moving on to optimization, we modify the existing code slightly as the images here. The lines in the FlexPD code have placed the index values corresponding to the elements in Python list. The necessary modifications involving changing the values. The FlexPD code now modified is integrated to Python code, which is split into various modules for future design tasks. Time dependence analysis is an attempt to study the effects of temperature and deformation on cantilever was abandoned due to the lengthy simulation times. Even with time-dependent simulations, multi-threading was implemented but did not significantly improve the computation time. The range of computations for analysis was determined based on the constraints of maximum and minimum polymer thickness. Initial 20 data points were generated using linspace function NumPy, but subsequent runs using small ranges were higher resolution near the maximum. The n-grid was set to 13 but increased to 20 for vibranium due to data issues. The higher n-grid values can improve accuracy, but time constraints limits further simulations. The code was designed to sweep through range of components thickness of limits of 7 points in each dimension, resulting in 343 points per material. To work within the limitations of the software's students edition and accounting for manufacturing tolerance, the values fed to FlexPD were rounded up precision of 1 micron, which produced better results. The code utilized the threading module to run 50 FlexPD scripts simultaneously in separate threads, taking advantage of the parallelization to improve performance. This displacement data from each output file was extracted to save in a list along with corresponding polymer thickness and orientation. The plots were generated using raw data without curve fitting and gradient set. So in this slide we see our maximum values for brass. In this slide we see our maximum values for vibranium. In this slide we see our maximum values for titanium. In this slide we see our maximum values for gold. So in summary, the optimal material properties for achieving maximum displacement in the device were found to be gold with specific thickness on the top, bottom, and side. However, due to the limitations such as rounding to 1 micrometer and using raw data with further refinement, the results should be taken in with caution. The simulation was conducted in 2D, which may have some differences compared to 3D simulation. Despite these limitations, the results can still be considered usable within a reasonable level of precision and can serve as a starting point for future analysis. Additionally, compromises were made in the project, and certain material like vibranium and tantalum alloy were found to have potential viability as substitutes. Further analysis may be needed in the future for more accurate results. Thank you.